Hello students and welcome to today's lab. And today's lab, what we are going to be doing is we are going to be working on determining the molar mass of magnesium using molar volumes. Okay, so what I've done here for you today is I've went ahead and made a demo version of this lab. And I've gone and included the first reaction, the most important reaction that we had here to start. And then we also made up some values for us to go off of here. Now, it should be noted that these values are completely made up, and they have no sense and have no meaning, and nobody should be using any of these values anywhere. Okay? So what I'm going to be having you do is, in the data analysis, it's wanting you to go ahead and plot this out. So the easiest and laziest way that we have to plot this out is to go ahead and put all of this into a Google spreadsheet and then make a chart. Okay, this chart is going to go ahead and plot it out. We're going to want to rename our chart here. And that's going to be the molar mass of magnesium. Okay. And then the next thing that we're going to want to do on our chart is we're going to want to make sure that we get a line, okay? And we're going to get that by going down here. We're going to get the trend line. The trend line finds the best fit line for everything here. We're going to go down here to label. Then we're going to use equation, and it's going to give us an equation. And this equation is the equation for this line right here, which means that we're going to be able to use this line equation to figure out our questions for going further on. And it's essentially y equals 526 times x plus 3.35. Okay? Then we're going to go ahead and go back. We're going to take this chart. We'll copy the chart. And we're going to put it right in here where it says to. We're going to paste the unlinked spreadsheet. And look at that. Look at that. That's some beautiful data. Okay, we made the best fit. Using your graph, calculate the mass, which would give you 24.00 centimeters cubed of gas. Okay, centimeters cubed is, our volume of gas. And this line is going up. Our y value is going up with this volume of gas. So we have 24.00 milliliters of gas equals 526 x plus 3.35. Okay? And now this looks like it's an algebra problem. Okay? So that means that we can go ahead and treat it as such. We can go ahead and say, oh, okay, well, this is 24.00 minus 3.35. And all of that is divided by 526. Okay. And we'll go ahead and just straight copy this into Google. And it's 0.03925. So this will answer our question here, 0.3925. Okay? And this is going to be grams, and we should put magnesium. Okay? From here, we're going to go ahead and calculate the number of moles of magnesium that gives this volume. Okay? So mass of magnesium versus moles of a gas. Okay? Now, this is 1 milliliter. Okay? So this is 1 milliliter of a gas. 1 milliliter is 1,000th of a meter. Okay? Therefore, since 1 milliliter equals 1,000 liters, we could go ahead and say that 24 centimeters cubed of a gas is going to equal, 1 milliliter, no, sorry, 1,000 milliliters, wow, I am tired, equals 1 liter. Okay. And if we know that 1 liter of a gas equals 24.0 liters, then we can determine that because this number right here is 1/1000th of a liter, that since this is 1/1000th of this one, since this one's also milliliters, that this number is also off by a calculation of 1,000. Okay? So here we have determined that this number here is 1/1000th of a mole of gas, and this was how much gas, how much magnesium was required to make 1/1000th of a mole of gas. Therefore, since this is 1,000 times smaller, this one's 1,000 times smaller. So that means that for 3, it would be 39.25 grams per mole of magnesium. Now, this is going to come into error here now, okay? Now we have to go ahead and calculate the percent error, okay? A reminder that our percent error is going to be actual minus expected, and then all of this is going to be divided by our expected. Oh, excuse me, I misspoke here. I want you to discount what I just said. It should be the opposite here. It should be expected minus actual or experimental divided by the accepted value or the expected value. And you can get those numbers from the table. Okay, these ones right here, 5 is basically asking you where you could have had some errors with your measurement because it's not going to end up being exactly the same. So you're going to always have a balance error somewhere, and that's usually whenever you're going to round. You're going to have a volume error somewhere, okay, and then you're going to have a total error, and that's going to be your maximum amount of error, so whichever is the maximum amount of measurement error divided by the mass that you weighed out, okay? And then number 6 here is just seeing what possible errors could have been made when I was doing the lab myself, whether you saw something going incorrect or if you were one of the ones that did the lab, what you may have done incorrect, okay? That's going to close us out for now, and as always, remember, be lazy.